using the using app, and just make sure don't point towards people.
I won't.
Okay.
They are my judges.
And you know, you have to introduce yourself, your name, and everybody's gonna you know which year, senior, major. Okay.
Okay.
A few words by yourself.
All right. Good afternoon, ladies and gentlemen. My name is Andy, and I'm a junior majoring in physics. So I'm gonna talk about the topics. My thesis is gonna centers around the physics major and I myself. So basically, this is gonna be like some thinkings while I'm majoring in physics. There are problems and questions that we encounter. All right, let's get started. So I want to begin by talking about why I majored in physics. So the reason I majored in physics are as follows. For example, I had no idea what to do as I just came out from high school. Unlike people, wait a second, my footnote is not being. Wait a second. Huh. All right, you see a footnote. I've seen people who always want to do physics, so which I'm very impressed and surprised. And we also heard that the physics is a field that gives you the ability to transition to other fields like CS engineering, like electrical engineering. And also I wanted to do a STEM major, and if it's hard and unique, that would be best. And then we've seen many successful examples and also what I call rumors. So rumor number one. So Wall Street hires a lot of physics and math PhDs, and they earn a lot of money. So this is a fact, but it's a little misleading, especially to high school students. They're gonna should be misleading by this this statement. For a quick quant history. So in the 1970s, that's Wall Street became a viable option for physics and math PhDs. And if you look at these funding people, they are like descendants of statistical physicists like Paul Arefes and also Gibbs, right? So Wall Street has like a relation with physics back in 1970s. And why Wall Street hires PhDs? So we are looking, because they are looking for these qualities from physicists. For example, independent research abilities, their skills, a strong quantitative background in math and CS coding, and also ability to work under high pressure. So I interviewed a renowned physicist. He is probably in this room, and he told me, so for experimental particle physics, one of the key, the most important abilities is that they're able to apply very complex models and analyze very large amount of data sets. So that coincidentally matches with what Wall Street is looking for. And then this is also a rumor that I found. This was a paper. It says compared to biologists, physicists were perceived statistically more competent. So we just ignore the latter part of this statement. We are gonna focus on the more competent one. Okay, so gradually as I learn harder physics, I myself begin to question and ponder this statement, the competence one. So am I competent enough? Simply put, am I smart enough? So what if I'm not? The solution is simple. We can redefine the smartness. We create a new word. It's called street smart. We assume the world is binary. It's either street smart or book smart. If you are not book smart, you are probably street smart. So there are other things that we are probably good at doing. Okay. So now I'm gonna I present to you this. I'm very proud of this. This is my mathematical definition of ACE. So we make these assumptions. So first, it's not the majors that make people successful, and successes are exponential. And then the older a person is, the more experience that person is gonna accumulate. And in the long run, given enough time, if he is eternal, you can eventually you will succeed. Okay, so I say success is basically a function of smartness. Smartness are very interchangeable here with strength. As long as you can utilize your strength, then you become smart. Okay, so right now we use success. We use omega to denote success, and we use E to denote smartness. And if you got a good grade from 406, you are probably gonna witness something here. Okay, this is my favorite model. So I say I put K as a randomness parameter. For example, it's gonna be luck. Okay, and T is age. As T increases, the chance you're gonna succeed is gonna increase. So there are many ways to utilize our strengths, and we know physics has a lot of pathways after they graduate. So it is also this wide range of options that make us, a lot of us, for example, me, uncertain about where we are going in the future. So right now, let's look at some statistics about we physics majors. So here is a 3 graphs about the PhD granted by subfield. So I'm not gonna spend time zooming into every single one. So we just look at the trend. So over the time, condensed matter physics always leads. It's always the most. And then astrophysics, astronomy, cosmology. Recently, it just started to pass to surpass particle physics. And then there are some fields that have disappeared, maybe absorbed by other fields, and some fields start to appear. Okay, so here's the industry distribution, the placement, the breakdown of physics graduates. For example, we look at the bachelors, they go to engineering, programming, finance, education, and research. So PhDs they go to like study different fields, so you have a different distribution. And the reason that people leave physics, and especially they abandon physics, is one of the most important reasons are money and interest. And we cannot deny that money is indeed very important, unless you have very strong perseverance, right? And the second, I think, is very important to that is interest, and you also have other factors. So speaking of interest, I want to quickly, okay, I want to quickly, okay, this is supposed to be money, okay? This page was wrong. I want to quickly compare a Google software engineer, which is a very common job for people to do after they graduate, compared to a physics graduate student. So we say, the median compensation for a software engineer is typically $300K, right? But we only consider the basic salary. So for example, SWE2, software engineer 2, you have a base salary of 140K. However, for an engineer 3, it's 180K per year. Okay, so we only consider the base salary here. Now we consider, now we just compare to the stipend of graduate students. For example, Rackham states they have 36K. So we just look at this box plot, and then we take an average. We say, we make these assumptions. For example, the PhD typically it takes 5 years with an annual stipend of 40K maximum, okay? And then bachelor's usually starts from SWE2. However, it typically takes you like 3 years to get promoted to SWE3. And we can plot a cumulative salary trajectory using this piecewise functions. Okay, and then we also assume no bonus, no stock equities. Actually, those are where the most money comes from. Okay, so we can plot a cumulative salary. And then we compare working as a software engineer directly after you graduate. In an 8-year period, you gain like 1.3 million. It's like twice as much as you can get after you get a PhD. So this model is definitely defective. So I fail to consider a lot of other important factors. For example, I completely ignore the living expenses, and also, going to different fields, you gain different things. For example, if you work, you will learn more about the workplace politics, and that's an important asset. For example, if you are a PhD, you will also gain independent research abilities. That's also important, and those cannot be monetized. Okay, but the consensus is the conclusion of this model is being a PhD student in the short run, you are more economically disadvantaged. So when you graduate with a piece of diploma in your hand, you're likely to see your peers already being, VPs on Wall Street, and rich software engineers enjoying the sunshine of California, and that's very possible. And they're likely to have wives, husbands, and children. And then the question boils down. You might question yourself: is a PhD worth it? Okay, so in the long run, I don't know. Here is a code I copied from Stacks Overflow. I forgot to cite, sorry. So basically, there's an algorithm on what you should do, how you should decide your career based on what you like to do and perhaps your strength. Okay, so you can take a look. I'm not good at coding, so I don't want to explain this. Okay, so now it's interest. So this semester I did something a little differently. So I worked as a intern for this venture capital. This is an accelerator. I work remotely. So in my first 24 days, I need to explain what an accelerator is. So we basically invest and help early stage startups to grow and expand. So we invest money and then we also help them as a co-founders. So basically, what I do is I talk to all sorts of founders. I talked to like 23 founders in my first 24 days. And one example I want to share is I spoke to a founder. He built a website, a website to increase the working efficiency of accountants. And then I saw a post from LinkedIn. So that guy claimed they received more than 2,500 applications. So I asked him, I DM'd him, like, how many are you actually gonna recruit? They said only 5 people. So looking at this statistic, probably PhD is slightly easier. Okay, so we are gonna revisit statistical mechanics, which I have mentioned before. And I'm not gonna go through the details. We are gonna just quickly skim through it and see the main concepts. Okay, so
the 2 minutes warning.
I'll be quick, okay? So this is the starting example. We cannot model like a single mole of gas because I have so many particles. So what we do is we look at the average, how it behaves globally, right? So we do not consider every single molecule. I'm not gonna explain what microstate and macrostate is. Basically, microstates we assume are equally probable. However, macrostates are specific configuration, how many heads and tails, and they are not equally probable. So we are gonna put 2 systems into thermal contact, E1 and E2, and we make these important assumptions. So given enough time, this is called the ergodic hypothesis. Given enough time, the system will explore all possible macrostate and finally settle down into one. So it will try to maximize the number of microstates. So to maximize, we take a derivative and then by product rule, and that's very simple. I'm not gonna go through the derivation. And we achieve the equation 6, okay? And equation 6, and then we can, because they are at the same temperature, we can define temperature and Boltzmann factor. And that leads to the statistical definition of temperature. And you can see it's very similar to what I have derived, just like a QCT and QED. This is merely a carbon copy of mine, okay? And then quickly, ensemble, canonical ensemble. So we now place a system in contact, thermal contact with a heat reservoir. So heat reservoir has a lot of energy, so you're not gonna affect it. So this assumption we make is for each lot of energy, there's only one single microstate. So it's just very comparable. However, this time the omega 2 is 1. So we perform a Taylor expansion because epsilon is much smaller than E. Okay, I will end soon, okay? And then when we take the Taylor, we take the Taylor expansion and then we raise everything to the power of E. Finally, we achieve this Boltzmann distribution. And later on, we can also derive the partition function, which is the denominator of the Boltzmann function, the normalization factor. And then after that, we have grand partition function and everything. So this is how we derive the statistical mechanic. We have a generalization of microstate and macrostate. Then we define the temperature of, we have a statistical definition of temperature for the thermal contact. And then for the heat reservoir, the ensemble average, a canonical ensemble, we have the Boltzmann distribution, that's grand partition function, and other concepts, thermal statistical mechanics. Okay, just like that, we derive we first redefine the smartness, okay, the intelligence, book smart, street smart, and then I got a mathematical definition of the age. And then after I retire, I will probably work on other distribution and functions. So yeah, we'll wait for it. So basically, the conclusion is when we are coupled to the real world, we can treat it like a heat reservoir. So we are not going to affect it too much. But the things that actually happen is actually the macrostate. So I always tell myself to believe in this. So what really actually happens is not only the most probable one, also is the best one. So this statement gives me some optimism sometimes when I fail. Okay, and disclaimer, this is not a lesson to success, and the models are fun and effective, so please part them as smartness. And good luck on your finals.
So how many are you going to PhD program after this talk?
It's too late now.
Too late now. Okay, thanks. And next.